Okay, so this is the last of the lectures where we have to be extremely careful about what do we know, and just proving things in order. At some point, we're going to be talking about closed curves. There's a really nice appendix in the book about the Jordan plane curve theorem that says if you have a simple closed curve that doesn't intersect itself, it divides the plane into two regions, the interior and the exterior. It turns out this is surprisingly difficult to prove rigorously. There is a joke, I'm not sure if it's true, where someone was taking their oral exam to get their master's, and they were asked, can you prove the Jordan plane curve theorem? And the response to the professors was, can you? At which point the professor said, oh no, crap, now how do we do this rigorously? And there's a lot of results in mathematics that just seem really clear. When we're proving things in this class, a lot of times I will just assume a result like that because almost always all the curves we look at are going to be circle, rectangle, maybe a triangle every now and then, but now that we've shown that things from triangles imply things for squares and rectangles, we won't do too much on that. So we will, for the most part, concentrate on the simpler curves and the simpler contours. Those are the ones that arise in practice. But you can prove things in greater generality. So the big result we want today is that if you have a holomorphic function on a disk, so we'll call this a theorem, f holomorphic in a disk implies there exists a primitive. So remember, primitive is the fancy way of saying there's a function whose derivative is equal to little f. Not surprisingly, we will call this function big F. Exactly. This is like a Dr. Seuss, right? You want notation so you can glance down and see what's going on. So we'll use the capital letter to denote the antiderivative. Is the antiderivative unique? No, we could always shift by adding a constant. Since we really only want to use this to integrate things, we're going to be integrating things along paths. The plus constant will often cancel out. So we're going to define a function big F. And then we'll show that that function is the primitive. So proof. So here is our open disk with some imagination. Without loss of generality, let's assume the disk is centered at the point 0. Right? I can translate everything. It's not going to make a big deal. This just simplifies the proofs. Let's say that this is some point z over here. I'm going to define my function f by integrating along this path, and I'll call this path gamma sub z. So we first go however far we need to go horizontally, and then we go however high up we need to go vertically. And so the definition, this is our candidate, is f of z is defined as the integral along the path gamma z of f of w dw. I have to be very careful. I can't write f of z here because z is the special point. Does this depend on the path I take? Do I have a choice of path in how I've defined it?
And how you define it, and the path is defined.
Right, the path is defined. The path is specified. I must integrate along this path. Many of you probably don't like being told what to do and would like to consider another path. You might want to go up and then over, be rebels. Are you allowed to define the function? Absolutely. Will those give the same answer? Should they give the same answer? Yes or no? Do they have to be the same answer? So one thing is, it should probably not depend on the path, so it should be the same answer. A weaker statement than it should be the same answer is what? How close must it be if I chose another path? Different by a constant, right? Now, you would like it to actually be the same answer, that it should be independent of path. But it should at least be the same up to a constant. Okay? Then you've got to be very careful, well, what do you mean by a constant? Is it the same constant no matter than which path you take? All that matters is whatever path I take to this, well, wait. If it's differing by a constant, I'm only looking at one value because I fixed z. So it should really be the same. What that would be essentially the same as saying is if I'm going through it like this, I now have a closed curve, and I'm saying the integral of a holomorphic function on a closed curve is 0. So we already know that if there's a primitive, then if you integrate along a closed curve, you get 0. Since we're trying to use this to define a primitive, we should in the end be getting that the integral is path independent. And then once it's path independent, you can choose whichever path you want. So now we want to prove that big F is the primitive of little f. So what should we do? Take the derivative. So consider the limit as h goes to 0 of f of z plus h minus f of z over h. This is going to be the limit as h goes to 0 of the integral from z to z plus h of f of w dw divided by h. Is that true, or do we need to do some work? Let's think about what's going on. So here's 0, here's z plus h. Technically, f of z plus h is integrating all the way horizontally and then up vertically. F of z is integrating like that. So if we subtract, okay, this segment would be canceled. So let's think about what's going on. We're going to play the game of adding 0. I'm going to close this off, and I'm going to go through this in two different directions. And now if you look at what is going on, from the f of z plus h, we go like this. We're subtracting off f of z, so we come down this one, and we go backwards on this one. So we've now reduced to, that's what we want, the path from z to z plus h, but we also have this rectangle. What do we know about the integral over that rectangle? It should be 0. Okay, why is it 0? It's good. This is 0 from Grossart. We showed that if we integrate a holomorphic function along a triangle, it's 0. And then we showed as immediate corollary, we also have it for rectangles. If you do not like the immediate corollary, draw a diagonal. Okay? So now we know it is legitimate to consider that path from z to z plus h. And the path, here's gamma of z plus h. That's the path we're going to be looking at. Okay? So all we have to do is show that in the limit, this is going to converge to f of z. This seems quite reasonable that it should be converging to f of z. This path should be extremely small. And since the path is extremely small, f doesn't really vary much. So I should basically be able to pull out an f of z. And then I'm integrating dw from z to z plus h. Hopefully that should just be h. Hopefully integration works the way I would expect. H divided by h is 1. So that's the rough idea of what's going on. Okay, so now let's look at what's going on with f of w. So we can write f of w as f of z plus, I think this should be enough, cz of w, where this is small. Times h. Well, I guess if I'm writing it as over here, I'm not writing like this. I'll just write like this. I'm trying like this. So why would something like this be true? F of w is f of z plus something small.
Once h has gotten small?
Once h has gotten small. So for w close to z. Small if w close to z. So why should that be small?
It's holomorphic, so it's continuous.
Good. It's holomorphic, so it's continuous. So we actually don't need the strength of holomorphicity. That's why I started to write the h. It's just force of habit. My function's differentiable. Let me start by doing, a poor man's Taylor series and do, a few terms. I don't need that. Continuity is more than enough here, because the length of this path is going to be small. It's going to be on the order of h. I don't need to have extra savings. So all we need here is by continuity. This is by the continuity, bless you, of f. So now we can go back over here, and now let's plug that in. So what do we have? So this is going to be the limit as h goes to 0 of the integral, we'll call this the path gamma z plus h, f of z plus cz of w dw divided by h. Okay, this is a constant, so we can pull it out. And now we're just integrating the function 1. Can anybody give me a primitive for 1? No. It's not z. It's w. Because w is the variable of integration. So because w is the variable of integration, this is just the primitive of f of z is just f of z times w. And then we just subtract z plus h minus z, and then we'll get h. Divide by h, we just get f of z. So this is going to just be f of z plus the limit as h goes to 0. And now on this part, we can pull out the maximum on the path, gamma z, z plus h of cz of w times the length of that curve divided by h. So the length of gamma zh divided by h. The only thing now that we have to be a little bit careful about is just how we're writing things. Because now I've basically taken absolute values for the error. And I no longer have inequality. So what I need to do now is to do it carefully. What I can say is the limit as h goes to 0 of f of z plus h minus f of z over h minus f of z in absolute value is less than or equal to. So it's just, I need to be a little bit annoying. It's clear what's going on, but you have to write it carefully. I want to just show that this piece is small, so I'll take this part, which is nice, and subtract it from the left-hand side. So now all we need to have is this go to 0. So the question is, what is the length of the path divided by the absolute value of h? So it's always greater than 1. So the question is, how much greater could it be? So the maximum should be square root of 2. So if you think about what's going on, if you write h, say, as hx and hy, here's the hypotenuse. So the length of the path is hx plus hy, or absolute value hx plus absolute value of hy. The length of h is, however, the square root of h of x squared plus h of y squared. So we need just some weak control, I almost use profanity, of this result here. It does not have to be strong, because this is going to 0. All we need to do is show that this is bounded. And so the question is, what's the easiest bound you can come up with?
So we could just say it's less than 2h?
Why is it less than 2h?
Yeah.
So triangle inequality. So we know the sum of any two sides of a triangle is greater than the third. So we know this is at most h of x plus h of y. Right? So the length will be less than or equal to hx plus hy, which will be less than or equal to twice the maximum of hx, hy, which will be less than or equal to twice the square root of the maximum of hx, hy squared, which is less than or equal to twice the square root of hx squared plus hy squared. And that's the length of h as opposed to the path. So that will get us a 2. Can you do better? Almost surely. Right? But there's really no need. And you want to get a sense when you're doing advanced theoretical mathematics, how clever do I need to be? Does this constant matter? Imagine you were trying to decide something about the rate of convergence. Then this would matter. But if all we're trying to do is saying we're going to take something in the limit, I don't really care what's happening at any finite stage, I only care what happens in the limit, well, I don't care if it goes to 0 or twice 0. So this is less than or equal to 2, and this goes to 0. So this finishes the proof. Okay. Any questions about this proof? So we've now shown that there is a holomorphic function that has derivative little f. And it's defined very nicely. You can begin to see now how the geometry of the sets matter. We're working in an open disk because we always want to be able to make these paths. What set could give us trouble to define a primitive?
So like if z was on the boundary.
So if z was on the boundary, we might be able to be okay if z is on the boundary because we just have to restrict z plus h to be inside. There's always issues when things are on the boundary. This is why you frequently say, let's just assume it's holomorphic, not just on your set, but on a small open set containing it.
If it's not convex.
If it's not convex, okay. So can you give me an example?
I don't know if you figured
I'm sorry?
horseshoe or something.
Okay, so imagine we had a horseshoe. Or, in honor of Homer Simpson, imagine we had a donut. Right? If we have something like this, how do we define our path? We have to be integrating in, so where do we start? Could I take something here and define a path from that fixed point? So I agree that if we now have something like this, I can't do straight paths. What was really nice is that, look, I'm from Boston. I hate New York City, but I have to admit there's one thing a subset of New York City does better than Boston. What is that? If you say baseball, you will fail. The grid. Manhattan is a beautiful grid system. If you ever travel in Boston, you will have the streets flip as to which one is above the other. They'll cross, and then they'll become parallel again, but flipped in orientation. Boston is a nightmare to get around unless you know the geography. What's so nice about a circle is I can say, look, go east-west, then go north-south, and you will get to where you need to go. In something like this or this, the path is much harder. If it's a set like this, I can actually still come up with a path. And what you might get is you might get a different primitive depending on where you start. That's where the plus c is going to come from. Each point in the set is a perfectly fine place to start. So how many of you have heard about pathwise connected sets? So a set is pathwise connected if you can get to any point in the set from any other along a path. It's convex if the straight line path is always entirely contained in that set. So the circle is convex because given any 2 points, the path connecting those 2 points is entirely in the disk. These sets are not convex. You have to leave the set to go along the straight line connecting them. So the idea is to now take this result and push it a little bit further to get Cauchy's theorem. So we just proved that if you are holomorphic on a disk, you have a primitive. And if you integrate a function that's holomorphic along a closed curve, you get 0. So now we want to push that and say, if you have a holomorphic function on an open set, and it's defined in the interior of the curve, and it's holomorphic in the interior of the curve, then the integral is 0. And so that's going to be Cauchy's theorem. And the danger is, what do we mean by the interior of a curve? And this is where, I mentioned, I think it's Appendix B. It's been a while since I've looked. It's the Jordan plane curve theorem. If you like topology, if you want an extra credit assignment, if you want to do a project for this class, understanding the Jordan plane curve theorem is a great choice. I've had some students who really love topology and have wanted to do that in previous years. It's too far afield. It seems intuitively obvious. Enough mathematicians have checked it. I'm willing to just use it. If you draw a simple closed curve that doesn't intersect itself, it splits the plane into two regions, the interior and the exterior. Yes, but it needs to be rigorously proved. So Cauchy's theorem. And there's a lot of different ways to state Cauchy's theorem. I think I just want F holomorphic on an open omega containing a disk V. Yes. So F is holomorphic on an open set omega containing a disk D. Gamma is a closed curve, then the integral along gamma of f dz equals 0. So I like to put the circle along my integrals to just denote the fact that it is a closed curve. A lot of people don't bother doing that. It just looks like we're drunk at the angle it's at. Okay. So the question is, have we proven this already? We're very close to having shown this. So imagine we have, here's an omega. We have some closed disk D. Gamma is a closed curve inside D. Here's gamma. And here's our D. Well, we now know that f has a primitive, right? So proof by previous, there exists a primitive. And now we're done. So in this situation, we're okay because we are looking in a closed disk. The challenge is, what if we remove the fact that it's a closed disk? What if we just say there is a closed curve and f is holomorphic in the closed curve? And so by that I'll mean on the inside and a small little neighborhood containing it. That's the generalization we want. So for example, so here is some curve. And let's say f is holomorphic on some open set containing the curve. So I have holomorphic inside the whole region. I have a holomorphic just a little bit past. I have holomorphic just a little bit inside. But I don't assert that it must be holomorphic in the entire region inside, because this is not inside the curve. There's this little slit that allows me to escape out. Now, of course, I could take the limit as that thickness goes to 0, and then I really would have this like bubble inside, where I would be asserting it's holomorphic if I extend just a little bit, but I'm not assuming it becomes holomorphic all the way through. What do you think will be true about an integral in this case? It's 0. Have we proven that? Because before we had to say it was living in a disk and it was holomorphic inside the whole disk. Can somebody give me a function that is not holomorphic inside a disk everywhere? What's our go-to function that blows up? 1 over z, right? If you need a function that blows up, all of complex analysis comes down to integrating 1 over z, right? So let's say that this is the point 0 here, and I give you the function 1 over z. We've got to be careful because the integral of 1 over z along a circle is not 0. But if you look at what's going on, I'm essentially going around that point clockwise once. I'm sorry, counterclockwise ones and clockwise ones, and they'll cancel. That I'm not asserting that the integral of 1 over z is 0 over this curve here, just the circle around the origin. I'm asserting that the integral is 0 along this bigger curve. So what we could do is we could do a bunch of small steps. And so we know that if you have like a small disk, it's okay. Does it have to be a disk? Could it have been a rectangle? We can do stuff like that. We can chop things up like this. And then each one of these will have interior, exterior, and they'll cancel as we go from one to the other. And then you just put all these pieces together, and you'll get that the integral will be 0. You've got to be careful and make sure you match up and have the same primitive as you go from one to the next. But this is essentially the bookkeeping you need to do to push it forward. That it's okay because we are looking at a region where the function is holomorphic inside that curve. It doesn't matter that it's not holomorphic at this point here. If you look at what's going on, we have almost like a hug, the hands are almost touching like this. This point is outside the curve. The interior of the curve is just this region in here. And even if we collapse this to 0 thickness, we would still be okay. The interior is still just the region between them. And then the whole point is in the limit, these two are going to cancel with each other because they're opposite orientation, and you'll get the integral along the outside curve, oops, I drew this out the wrong way, is equal to the integral along the inside curve. That it allows you to just collapse things downward. Okay? Now you can start to what if I put an Astley curve over here? That's oscillating maybe infinitely often. What's going to happen in a situation like that? This is where I'm not going to go into all the technical details of the Jordan plane curve theorem and the interior and the exterior. But this is basically what's going on. And for the simplest situations we're looking at, these toy contours that the book talks about, we're fine. So for us, we're going to be looking at rectangles or circles or things like that where you have a finite number of points that you blow out. And so what we'll often do is we'll have maybe the function is holomorphic everywhere except maybe at these points. So you would be going around, and then you would come here, go around, and come back. You would travel this side twice in opposite directions, so it would cancel, and then you would do the same thing at all these other ones. And then you would have that the integral along the outside would basically be the sum of those integrals. And because you're going along the outside counterclockwise, when you come in all of these, we're going to go around these counterclockwise. The sum is 0. I need to make sure I'm doing this right. Okay. And the sum will be 0, and then we just worry about switching them over to the other side. So we might have to worry a little bit about the minus sign. We'll do that when we state the theorem in full generality.
I don't understand. In this one, aren't you traveling like 5 times counterclockwise, but only once clockwise, or?
So I come down here. No, I come down here, and then I come up this one.
Yeah.
And then I would probably choose to go around this one clockwise.
Oh, so you just alternate every time?
No, and right, I'll go around this one clockwise and then come down. So this one I've gone up and down, so this one cancels, and then I do this clockwise. Because I'm just traveling like this, and then that way I keep everything inside. I want to keep the region to the left as I walk around. So I'm walking around, the region is on my left, I come up. To keep the region on my left, I have to go clockwise, and I come down. And then I come over here, I go clockwise around.
I just thought the intuition behind the first example was that like the slit goes to the limit and that cancels.
Right.
The outer and the inside go to the limit.
Well, but the outer and the inside have opposite orientation.
Oh wait, I guess if you break it up.
Because I'm keeping the region on my left as I walk around. So because I keep the region on my left, I'm going through all of these counterclockwise. Oh, sorry, going through all those clockwise. And so for this one, right. So because they're all going through clockwise, they all have the opposite orientation. So the sum of all the integrals is 0. And so since the sum is 0, when I put the clockwise ones on the other side, I get a negative sign. And now they become counterclockwise. And I'll get that the integral along the outside is equal to the sum of the integrals along the ones that blow up. Now, what would happen if these lines crossed each other? Does it matter? Is it always possible to choose lines like this that don't cross?
Even if they cross, would it matter because you're canceling them?
You're canceling them, so it doesn't really matter. But in terms of then what your curve looks like, you now have an intersecting curve. And so it's not going to matter. If you only have finitely many points, it's not going to matter. I just want to be very honest with you whenever I'm trying to put something by you. And just flag where you have to be just a little bit careful. And you have to just ask yourself, does it matter? If there's only finitely many places that blow up, can I always just adjust my path accordingly so that they don't cross? What would it mean if it blows up infinitely often? Well, it turns out if it blows up infinitely often, strange things are happening, and we don't have to worry about that. So we will write this down very rigorously later. I just want to give you a sense of what we're building to. We're building to taking a curve, and if the function is holomorphic except at finitely many points, we reduce the integral of the curve to a sum of integrals of small circles centered about the points where the function blows up. And then we just have to figure out what those are. For each one of those, we do a Taylor series expansion of the function. And we show that the integral of z to the n along a closed circle is 0 unless n equals -1. So it's all going to come down to just how the function blows up at each one of those. If you integrate 1 over z squared, it's 0. If you integrate z to the 5th, it's 0. If you integrate 1 over z, you get a contribution. So this is giving you a sense of where we're going. What I'll do is I'll state Cauchy's formula, and then we will move and we'll start doing some examples. All right? We will prove Cauchy's formula probably very rigorously on Wednesday. I want to state it right now just because it is such a great result. Now, right now, who's winning in terms of references, Cauchy or Riemann? Yeah, Cauchy, right. In the beginning of the semester, Cauchy is just on fire. By the end of the semester, Riemann will get back into the game. Sadly, he died far too young, and so I think Cauchy will win in the end. Okay. I'm sorry?
You're giving away the end.
Oh, I said I think. We could always choose to emphasize certain things to give Riemann a fair chance. And then the other thing is, are you going to really call all theorems equal? I mean, we got the Riemann hypothesis. Have you ever heard of the Cauchy hypothesis? No, absolutely not. And so when you think about what's inspiring mathematicians for hundreds of years, I mean, Cauchy's nice, we use it all the time, but it's a tool. Whereas Riemann. All right, so again, the problem with Cauchy's theorem is always what conditions do you want? We'll say F is holomorphic on an open omega that contains some disk D. Then f of z is 1 over 2 pi I integral of gamma of f of zeta over zeta minus z d zeta. So I'm going to just state the result today. So maybe if you want, gamma equals the boundary of the disk D. This is an absolutely shocking result. What it's saying is the following. Here's some big set omega. Here's a disk inside omega. Here's a closed curve, gamma, the boundary of the disk. If I wanted to find z, so we'll have here z is inside the disk. If I want to figure out what is the value of my function at z, what information do I need to know? I just need the boundary values. It tells you it uniquely fills in. When you specify what's going on the boundary, the interior values are uniquely determined if you assert that your function is differentiable. That is a strong condition. Can you give me a differentiable continuous real valued function where you specify the boundary but the inside is very different? Sure. We have lots of different choices as to how we fill things in. But if I want the function to be holomorphic, this is telling us there is a unique choice. All that matters is the boundary values. Now, for the function to be holomorphic, I need a little bit more than just what's going on in the boundary. I probably need some small little sliver neighborhood so I have an open set to deal with. But it's telling us that it uniquely fills in. Absolutely shocking result. So we will prove this result on Wednesday, but I want you to at least be thinking about this, and when you're waiting in line at Whitman's, whatever, how could this be true? The other thing is, if you think about physics or chemistry, this has some really nice applications. If I specify the heat, say, on the boundary of a region, should the equilibrium state be uniquely determined? One would hope. That there's not many different ways that, well, on Monday, Wednesday, and Friday, the disk chooses to come to this equilibrium. On Tuesdays and Thursdays, it comes to this equilibrium. And on the 4th leap year, following a presidential election, going to, you don't want something like that. A lot of these results are used in solving physics problems and related to certain differential equations. So I want you to have some sense of where the stuff is lurking in the background. Okay, so this is Cauchy's theorem. So what I want to do now for the rest of the day is do an integral. The book, the first one they do is related to the Gaussian, and it uses the fact that the integral of e to the negative x squared is well known. And you can do that with polar tricks and whatnot. And then it uses that to get the Fourier transform. So that's a good example to read. I want to talk about one or two other ones. So I want to look at, as an example, the integral from minus infinity to infinity, 1 minus cosine of x over x squared dx. So for some reason, I want to evaluate this integral. What's the first thing you need to ask whenever you see an integral? Yes. Does it exist? Well, there's two places to worry. What's happening near x equals 0, because I've got a 1 over x squared, and what's happening as x gets very, very large. Well, since cosine is bounded by 1 in absolute value, the numerator is at most 2. It's going to decay like 1 over x squared, so it has good decay at infinity. I'm not worried about infinity. Near the origin, cosine of x looks like 1. Okay, we've got 0 over 0, so we use L'Hopital's rule, or we Taylor expand cosine of x, and we get 1 minus x squared over 2. So the 1's cancel. So near the origin, this looks like a half. So it's going to be integrable, so at least it makes sense. There are two ways you can try to evaluate this integral. One is we need to find some function of a complex variable that's related to this. So one possibility is to say, look, we've got the function f of x is 1 minus cosine. Cosine is e to the ix plus e to the minus ix over 2 divided by x squared. Can anybody think of a function of a complex variable z that looks like this? What should we do? Yeah. Send x to z. That's a really good recipe to suggest a function to look at. And then when z is real, it will reduce to our original function. The other approach for this is to say that what we have is f of z is 1 minus e to the iz over z squared, and we have the real part. So e to the iz is cosine z plus I sine z, and so this would just basically be integrating the real part. So either approach is fine. if you use this approach, we have to be a little bit careful. One exponential is going to be blowing up in the upper half plane and going to 0 in the other, and the other one is going to be flipped in terms of which way it goes. So we want to figure out what kind of contour to look at. The troublesome point is the point 0. The function blows up at 0. So the contour is choose something like this. And then we can take the limit as epsilon goes to 0. So here's epsilon, and here's the origin. If I looked at the first choice, as I take epsilon going to 0, it doesn't really change the value of the integral if I throw away the value from negative epsilon to epsilon. Right? This function is nice and continuous. When x is very close to 0, this function is looking like a half. So I don't really worry too much about that. And now what I want to do is I want to look at what happens if I try to integrate everything else. Imagine this is maybe plus r here, this is minus r, and I have a big semicircle like this. If I want to look at the function 1 over x squared and ask, how much can 1 over x squared give me along the semicircle? Well, this would now be 1 over z squared. So in absolute value, what's 1 over z squared on the semicircle? What's its absolute value? 1 over r squared. What's the perimeter of the semicircle? Pi r. So the contribution of 1 over z squared is going to be bounded by pi r over r squared. It's going to be bounded by some constant over r. It's going to tend to 0. I don't have to worry about the contribution from that. What about integrating e to the ix over x squared? Now let's look at e to the I z over z squared. This is e to the ix e to the minus y over x plus iy squared. If I integrate this function, what am I going to get? Well, since I'm on the semicircle, x plus iy squared is going to be basically besides r squared in absolute value. How about how large e to the ix e to the minus y is? It has magnitude 1. What about the exponential decay? I like exponential decay. Exponential decay is wonderful. Do I have exponential decay everywhere? I do, but how small could y be? No, if y is as large as r, then I have huge decay.
Sorry, y could be as small as 0.
Y could be as small as 0. So this part here is not giving me exponential decay, unfortunately, until I move up a little bit. Sometimes later in the semester we'll draw maybe like a theta, where theta is like maybe 1 over r, or 1 over square root of r. So if you move up just a little bit, you have decay, and you have a small segment length there.
This is really simple, but why is I multiplying the x value with the y?
Because z is x plus iy. So you get ix plus I squared y. And so this is going to have plenty of decay because we have the z squared down below. All we need to know is that the numerator is not blowing up. So this piece is fine if we integrate up top. Okay. What about the e to the minus ix? So the e to the minus iz over z squared. This is now e to the minus x, minus ix, and it's going to be e to the y over x plus iy squared. So what's going on with this piece? Is this piece okay along that circle? I'm sorry? No. It's exponentially blowing up. So this is an exponentially bad choice. What you can do is you would have to split this up almost into two integrals. One integral we're doing along this, going in the upper half plane, and then the other one for that piece you would have to do in the bottom half plane. And then we also have to worry about what's the integral over this small little piece over here. Oh, it doesn't matter, it's small, it has length on the order of epsilon, right? Do we have to worry about this integral in the complex plane?
It's going up by 0, so maybe.
Yeah, because if we look at it now complex, what's going on as a complex function? Well, you now have to be a little bit more careful. And again, we're splitting things up. So let's say we're looking at the e to the iz. Well, if we have e to the iz, this looks like 1 plus iz. Oh, crap. The 1's cancel, and then we'll have like an iz over z squared. That's a 1 over z. 1 over z always contributes. And so we would have essentially half the contribution of that. So there's a lot of dangers when we work with something like this. So right now I'm just trying to give you a sense of how you do the calculations, what are the things you have to worry about. You want to show that a lot of things don't matter. Is the function holomorphic inside this region? Yeah, so the integral over the whole region should be 0. But it gets complicated because we're splitting things up bottom and top. So it might be better to look at this function. The real part of this integral is what we want. So let's just look at that. So if we look at 1 minus e to the iz over z squared, when we are close to z equals 0, we're going to get 1 minus 1 plus iz plus yada 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 over z squared, which is equal to I over z plus something nice. So near 0, this actually blows up and has a singularity. Now this piece over here is nice, so because it's nice, it's bounded. Then you integrate it over something of length on the order of epsilon. It's pi epsilon. So the integral of nice over that little semicircle is going to be on the order of epsilon. It won't matter. But the I over z will matter. Let's look and see what this is going to look like if we go on the upper half semicircle. Well, 1 is bounded by 1. E to the iz, we're in the upper half plane. So if I now write it like that, what would I get? E to the iz would be e to the ix plus iy, which is e to the ix, e to the minus y. So that's bounded. So the contribution from this piece is negligible. So what we can now do is we can now use Cauchy's theorem, and let's break it up into regions. We'll call this region 1, 2, 3, and 4. So the integral along this closed curve of gamma of f dz is equal to the integral along 1 plus 3 of f plus the integral, oh, that's no longer closed, plus the integral over 2 of f plus the integral over 4 of f. And what does the sum of these integrals equal? 0. And now 1 plus 3 in the limit is going to give us the integral we want. Or at least the real part of that will be what we want. And this is why this method is a little bit more annoying. What would be true about the imaginary part? So if we now have, oh crap, let's say z is real valued, so we'll have e to the ix, so we'll have cosine x plus I sine x over x squared. What can you tell me about sine of x? What kind of function is it? It's odd. And we're integrating from minus r to r, throwing away minus epsilon to epsilon. We're integrating over a symmetric region. Hooray, we don't have to worry about taking real parts. Because we're integrating an odd function over a symmetric region, that's going to just be 0. So in the limit, this is going to converge to the integral we want. This is going to become small. And all we have to do now is integrate f over that one little itty-bitty bit. So the nice part is going to be of size epsilon. And so all we have to do is we now have to integrate over 2 the function I over z dz. And so are we going clockwise or counterclockwise? Going clockwise. So this is integrating theta goes from pi to 0 of I over epsilon e to the I theta. And then the derivative is going to be I epsilon e to the I theta d theta. The e to the I thetas cancel. The epsilons cancel. I squared is -1. So the -1 means I can flip the order of integration, and I get a pi. And I seem to be off by a minus sign because I was pretty sure that the answer was pi, not minus pi.
Shouldn't it be minus I over 2? Because you have 1 minus 1 and then minus IZ. If you go back to the expansion on the left. Where you have that should be minus.
Good, there's a minus sign there. Excellent, good. It's a minus there. So there's the extra minus sign. So when we plug it in, this piece gives us a minus pi. Thank you. And so now we get that our integral is just equal to pi. So we have now evaluated this integral. This is a really good place to stop. That integral is pi. That's a tough integral to do with real values, with real variables. Okay.